and once, because time is short, if possible, I'll share a few more problems on AC circuit. But let us start resonance first. This was over from here. Resonance in. So whatever we have taken so far in AC circuit, we have taken RL and RC. Did I consider RC circuit only RC? No, na. Only RL I have discussed, or
Yes.
RC also. RC also I have discussed, na? I have discussed. Okay. So today's class will start RLC circuit. All these elements are in series. Okay. So then what happens? Uh, because of the resist, one of you are it's still unmute. Mute yourself. I'm getting noise.
Aryan, please mute.
Okay, so we have resistor, capacitor, and inductor in series, and we know that when it is a purely inductive circuit, then your inductive voltage will be leading and inductive current is lagging by 90 degree, and just the other way around in case of capacitor. These are already known to us. Now, what is the total voltage if you are applying here? That V is the phasor sum of this VR, VL, and VC, isn't it? So if we do that, we should, when we want to draw it, we should take here I as your reference phasor. Why? Because it is a series circuit and I current through all this element same. So we can take I as your reference phasor and we keep drawing the other voltages, which is your VR, VL, and VC, and then that will be equal to your V. Okay. So if it is a if is the case like this, say it is a more inductive, I mean inductance is more, capacitance is less, then the overall current will be lagging, uh, lagging the input voltage, isn't it? So if we do that, then say this is your reference phasor I series. Yet it is not mute. I am getting noise. Please mute yourself.
I think, sir, you can mute him if he is not muting himself.
Who is the person? Okay, let me, because I can see like that. Aryan Raj. Huh. Okay. So for this circuit, we can see only R, L, and X are shown. But if we want to draw the phasor diagram for this circuit, we can draw like this. We can take I as our reference phasor. Then what is your VR? VR is in phase, so we can take VR here. Then if your inductance is more than capacitance, then inductive drop definitely will be more than capacitive drop. So as we know that VL will be leading I by 90 degree, that means current will be lagging in case of inductive circuit. So we can draw VL like this. This is your VL. And then you have the capacitive part, where in case of capacitive circuit, VL will be VC will be lagging current by 90 degrees. So you should either draw from here or you can draw directly from here, which is VC. So from here you can draw VC, which is in the opposite direction. So this is your VC. So now phasor sum of VR, VL, and VC will give you your total voltage which you are applying here, supply voltage, which is V, because V is nothing but phasor sum of VR, VL, and VC. So you can see that here your current, series current, is lagging by an angle phi. So that phi angle is what it is. Basically we can write VR as I into R, VC as I into XC, or we can write minus jxc I xc minus j is equal to your vc, vl is equal to j I xl, and vr is equal to I into r. So if you just divide the summation is equal to actually your v, and then if you take I common, this, then this is I into r plus j into xl minus xc. Okay, so that actually give you the impedance for this circuit, R plus J into XL minus XC, that is your impedance, which is written like this, difference between these two. So your overall impedance is equal to root over R square plus X square. Okay, and what is this angle phi? It is X by R, or we can say it is cos inverse theta, phi equal to cos inverse R by Z, where Z is equal to root over R square plus X square. Okay, so this is the case for the RLC series circuit. Now say we are having a, variable frequency source, so we are applying AC source, but frequency we can vary. Then what happened to the impedance? What is the expression of the impedance? What is XL? XL we know already, we have seen that XL is equal to omega into L, and XC is equal to 1 by 2, 1 by omega into C, isn't it? This is our XC and this is our XL. So if we write the expression in terms of mm, Z is equal to R plus J into omega L minus omega C. So, or if we want to write in terms of frequency, we can write it as R plus J into 2 pi f L minus 2 pi f C, if we really want to write in terms of frequency. So omega is the angular frequency, therefore it is 2 pi f, and f is the frequency in hertz. Okay, so now if we gradually increase our frequency, then what will happen? If we keep on increasing frequency here, from a certain point, your omega L part or 2 pi fl part will be increasing, and this part XC part will be decreasing. So circuit become more and more inductive. And if you keep on decreasing the frequency from a certain level, you will see that for lower frequency the XC part will be more and XL part will be less for the lower value of frequency, because for the low frequency this part is inversely proportional. So 1 by something lower value means this is high and this is less, so the circuit will become capacitive in nature. So if you keep on varying the circuit, you will see that the current plot phasor will be looking like this. So this is called actually circle diagram. If we draw, if we keep on varying the frequency, from low frequency to high frequency, when frequency is very low, then like tends to 0, then this will become infinite. So current will be very small, and it will be like this, very small but almost 90-degree. Then gradually if you keep on increasing the current, it will be capacitive in nature. I'm drawing wrong, actually I should use leading, because current will be leading for the capacitive part. So if this is your voltage, input voltage, current will be very small but 90-degree, and then gradually it is like this. When you keep on increasing frequency, the capacitive part is going low. So it's like that. And then one point will come where I will be in phase with voltage, because that time what happens, your VL will be completely nullified by VXC. So there will be one point where your omega L is equal to omega C for certain frequency. So for a given value of inductance and given value of capacitance, your entire J, this imaginary part, will be equal to 0. So the frequency will be what? Omega will be root over LC, and frequency will be what it is, f equal to 1 by 2 pi root over LC. So at this particular frequency, your current will be in phase with your supply voltage, and then again if you further increase it, gradually it will be lagging. So like that. And then one point will come when it is almost 90-degree lagging, but current will be very low that time, because omega here tends to infinity, this will be 0, this is very high infinity. So r, if it is 1 plus j infinity, that means very high impedance. So it will be looking like this. So your current phasor will be made by a, will be indicated by a circle like this. Okay. So with frequency, if you plot, you will get this kind of plot. So you can see that for certain frequency where V is in phase with I, or it is becoming purely resistive circuit, that frequency is known as the resonant frequency. Why? Because if you have a resistance which is of lower value, say you take a what should I say? You have a 50 millihenry, say your inductance, and capacitance is 50 microfarad. If you have this as a specification, and resistance equal to say zero point 0.1 ohm, so then what happens at resonance, your this part xc part won't, xc and xl won't contribute anything, because xc minus xl will be 0. So if you are applying a voltage source of 12 volt, you will get a current which is very high, that is 120. So actually we are not going to apply 12 volt, we'll apply some very small value, say 1 volt or even lower than that. So if it, or we'll use a higher resistance, so you can see that it, this time your current will be maximum, it will be very high. But for the, if you just shift from that particular frequency, then gradually your current is going very low. So there'll be if you plot with respect to frequency, this is your frequency and this is your current waveform. If you plot, then you will see that for some frequency it is abruptly going high, and then gradually it is again falling back. So that is why it is called resonance. What is the mechanical resonance? Anyone? This is your resonant frequency omega. So mechanical frequency, it, what happens when you apply a forcing function on a mechanical system, which is a periodic forcing function, where the input frequency matches with your the natural frequency of the mechanical element, then there will be a high amplitude oscillation, right? So that time the system can I mean there will be fracture in the mechanical system. So that's why it is always recommended not to march through any bridge, isn't it? Because of the periodic step, there will be a same frequency of the natural frequency of the bridge, so bridge will start oscillating with a very high frequency, and finally it can crash. So that is the concept of resonance. So it will, its amplitude of the oscillation will be going very high. So here also you can see that for this particular frequency, for the input frequency variation, suddenly at particular frequency, which is the natural frequency of this circuit, natural frequency depends on the L and C, that time your current waveform suddenly will be acquiring a very high value. So that is why it is called resonance. Okay, so electrical resonance. And what else? We can call this resonant circuit as an acceptor circuit. Why it is called acceptor circuit? Because you can see that for a particular narrow band of frequency, it is accepting the signal. So there your signal is getting amplified. But for the other frequency, it is low. It is very low, so it is attenuating actually. So for this zone of frequency, it is working as an acceptor circuit. It is accepting the signal. If you apply a signal to this RLC circuit, and if your current is your signal through it, then you will see that for the frequency which are like, for the selective frequency, it is giving you a high amplitude current. So that is why it is called the acceptor circuit, and it is used in the transistor in the transistors, or in the even in the television set, many places. Okay. Similarly, if you have the parallel resonance, when we'll study that, there we'll see that it is called a rejector circuit. Okay. So let
But
us
one
now.
thing,
Huh, yes.
sir, in the V part, that v is equals to IZ. So, sir, Z is changing because the frequency is changing. So, sir,
Hmm.
voltage should change. Now, why then the current is changing?
Now, if you apply a fixed voltage, if you just go through a fixed current, say you have a current source, then your current will not change, your voltage will be changing. but then what will happen, your voltage will be higher for the other frequency than the resonance frequency. Okay, but current will be, if you fixed your voltage source here, and you will see that your impedance is high for both upper and lower frequency of than the resonant frequency, so that time your current will be less. And when you have a resonant frequency, then L and C will cancel each other, so you have only resistor. And because of that, if you choose a sufficiently lower value of resistance, you will get a higher value of current. So then you will say that your current will be high. Are you getting now?
Yes, sir. Yes, sir.
Okay, so resonance, it continue. VL and VC cancel each other, two reactants together as a short circuit. It acts as a short circuit, no voltage drop across them. Because of this combination, VL and VC, they are actually balancing one another, neutralizing one another. So drop across these two together will be uh, 0. So that means it is a short circuit. So you are left with only V by R. And if your R is very small, it will be very high. Current will be very high. Phasor diagram for the series resonance is shown. This is the phasor diagram by this. How? Because you have no inductive part and no capacitive part. So it is in phase with the voltage. So current will be in phase with your voltage. So we can draw it like this is VR, and then this is VL, and then this is VC. So you are arriving at the same point. That is why V is equal to VR. Okay, in phase with current. Or we can say in other word, current is in phase with voltage. Calculation of resonant frequency already I have shown. Then what else? Let us go through. L is in Henry, C in Farad. Usually we won't get it Farad and Henry, either in millihenry, and this is in microfarad. This is the usual range. And then you can calculate from, if you substitute properly, you will get the frequencies in hertz. And if you multiply with 2 pi, you will get in radian per second. Okay. When a series RLC circuit is in resonant, it possesses minimum impedance that you can understand. It becomes, impedance become pure resistance because the effect of inductance and capacitance are nullifying one another. Hence, the current is maximum and it is limited by R alone. So current I0 is equal to V by R is in phase with V, and based on the choice of resistance, it will give you the thing. So if resistance is small, then you will get a plot like this with frequency. If this is omega, if this is I, and if resistance is high, these things will be flat. So it will look like this. So if this is for R1 and if this is for R2, then definitely just looking at the plot, we can say R2 is much higher than R1. And if you take ideally, if I mean theoretically, if you take R to be 0, then this will look like this. I mean infinite. Which never happens because resistance always have a wares always have some resistance. Okay. As the circuit current is maximum, it produces large voltage drop across L and C. These drops are equal and opposite, so they cancel each other. Okay. So there is no voltage across the part of the circuit consisting of L and C together, as I told. That is, circuit acts as a short circuit to the resonant frequency. Hence, a series resonance circuit, sometimes called acceptor circuit, and series resonance is often referred to as voltage resonance. Why they are saying so? Because it is uh, the voltage across inductance is nullifying the voltage across. It is just balancing the voltage at capacitance. And your series resonance circuit called acceptor circuit, when we apply a fixed voltage and keep changing the frequency, current will jump to a very high value at the resonance frequency. So that is why it is called, as you are applying a voltage, constant voltage with a variable frequency, you are getting this kind of response, means it is called voltage resonance. And in case of the parallel resonance, you will see that it will be called current resonance, because current will be current in the inductive part will be balancing the current of the capacitive part. So that is why it is called current resonance. If XL and XC are at any frequency f, then the value of the resonant frequency of such circuit is found to be uh, the relation f0 is equal to this. If XL and X0 are at any frequency f, then the value of resonant frequency. Okay, so this is actually Xc, we can write it as 1 by 2 pi f into c. XL is equal to, sorry, it is 2 pi fl. Then what we can write from here, Xc by XL is equal to, at resonance, what we can write, this is equal to 1. So we can write it as, it will be f square 2 pi whole square, 2 pi f whole square, isn't it, into 1 by LC is equal to 1. Anyway, I can't understand why it is written. Let me think over it. Next class I'll tell. I cannot make out what it is told by this relation. So it is saying that XL and XC are at any frequency f. So any frequency, it is like this. Then they are actually trying to substitute in the f0 how they are relating. I'll just think over it. I'm not very
Yes,
sure
sir,
about
sir.
this.
Sir, F0 is basically 1 by 2 pi root LC. So, sir, that they are substituting in this equation.
F0 equal
We
to
have 1 by 2 pi root LC, which we have
uh,
uh, generalized it. So, sir, here you can
yes.
say that XC by XL will be 1 by 4 pi square F square LC.
So here we can in case of L, we can write it as, okay, got it. Oh, they want to say like this. L we can substitute in terms of XC. So XC we can write here L as XL divided by 2 pi F, isn't it? And C is equal to 1 by 2 pi F into uh, okay. So XC is equal to 1 by 2 pi f into c, isn't it? So we can write c as 1 by 2 pi f by xc. So this 2 pi will cancelled out and we are left with f into. Okay, so what they want to say by this statement is you can express any resonance frequency by XL and XC at any frequency f. So this is the expression. So at any frequency, say f hertz, you know the value of XL and XC. So from there you can write your resonance frequency like this. Are you getting? Thank you. Your name, your voice I know, but your name I don't know. Can you repeat your name?
Sir,
Harsh, full name?
Harsh Kumar.
Harsh Kumar. Okay. Thanks for pointing out. I just got puzzled out at any frequency what they want to. It should be rewritten that if we want to express the resonant frequency in terms of XL and XZ at any frequency, the value of resonant frequency in such circuit can be expressed like this. I could not make out from this. Anyway, thanks very much. Okay, next is resonance frequency in RL circuit. This is a summary. So we are almost at the end position. We'll go for the mathematical analysis part now. When RLC circuit is in resonance, this we understood. Z will become purely resistive. The circuit current is maximum given by V by R. The power dissipated is maximum, which is I square R. Because this is now purely your power factor will become 1, isn't it? In resonance, power factor will become 1 because Z is equal to R. So you get the maximum power. Otherwise, what will happen? It is Vi cos phi. So cos phi is less than 1. That means it is less. So maximum thing is at resonance only. Maximum power consumption is at resonance only. Okay. Although VL is equal to VC, yet V coil is greater than VC because of its resistance at resonance. Why it is called so? Because there will be some resistance in the inductance which you cannot avoid. It is hypothetically can be resistance equal to 0, but small r should be there. That is why your VL will be greater than VC because of the resonance. Because at the resonance we don't consider the resistance of the inductor, so that if it is small r is there, then of course the drop will be like that only. And during the resonance current value, resonant current will be this r plus this small r. Okay. Okay, so this is all about resonance, and Q is equal to, I mean, your quality factor is equal to tan 0 degree, which is equal to 0. I think analysis is there in the subsequent slide. So resonance in RLC circuit, graphical representation we need to draw. As we can see from here, this is your frequency. You are gradually increasing your frequency from lower value to a higher value. This is your current waveform, and this is the plot for the current. So initially it is low, then gradually when you keep on increasing the voltage, it will be reaching to peak, right, at the resonant frequency, and then again gradually it will be going down at the higher frequency. So when you'll go to the higher frequency, this is inductive, and lower frequency, this is capacitive. So if you plot your impedance, this is Z is your impedance. So here it will be like this. So it is a rectangular hyperbola for the capacitive part, and when the inductive part is there, it will be little this, like this. So this is your uh, impedance versus omega or F plot, F versus impedance plot. Okay, so this is actually sum of, this is your R. So at resonance, when it is minimum, it should be equal to resistance of the circuit. And then this is your omega L, or 2 pi FL, 2 pi FL. And another is rectangular hyperbola, which will be going like this is your x, like it is shown here. Xc is shown in the below part. I am drawing magnitude wise, but they are plotting with as a j xl xc, that's why negative. So this is your xc part, and this is your effective this thing, your impedance. Okay. So when you're after resonant frequency f0, when you cross resonant frequency, it is inductive, and below resonant frequency, it is capacitance. So net reactance, if you want to see, it is given by XL minus XC. So graph is hyperbola, but it is not rectangular hyperbola. It and crosses x-axis at a point A where it is the resonant frequency. Because that time only you get the purely inductive thing. So it will be 0. Okay. This is rectangular hyperbola. Why? Because it is xc is equal to 1 by 2 pi fc. So 2 pi is constant, means it is if f is your dependent axis and xc is your independent, then it is of xc equal to xy is equal to c square form. So it's a rectangular hyperbola. But this one is not, because xl part has come. So this is your circuit impedance. All this you know already. At low frequency, Z is large because X is large. Since Xc greater than XL, the net reactance X is capacitive, PF is leading. So that is written here. I have written inductive and capacitive. Here they are writing leading, and the other part it is lagging, because XL will be greater than Xc at higher frequency. Current I0, it is the reciprocal of the circuit impedance. So when Z is low, I0 equal to high, and vice versa. And as seen, I0 has a low value on both side of F0, because Z is large there, and the maximum value at V by R. Okay, hence the maximum power is dissipated by the series circuit under the resonant condition that we have already discussed. Frequency below and above resonance current decreases, as you can see, and I0 is equal to V by R, and other than I0 it is V by Z, which is V by R square X square. So hence I by I0 is equal to, it is what? It should not be R by Z. It is V by R, V by Z by, so it will be that only, R divided by Z. And what is your Z? Z equal to 2 to the power R square S square. So X is the net circuit reactance at any frequency F. So that is actually difference between, X is actually 2 pi F XL minus 1 by 2 pi FC. Okay. So power factor also we can say that resonance it is 1, and then and here you can see that these are the two different plot we are giving. This is your cos phi. So cos phi is equal to 1 at resonance, and then it is going low, and when it is very when f equal to 0, then it is 0, and then when f tends to infinite high, then it is again approaching to 0. So this is how power factor will look like, and this is your current, and this is your impedance. Okay. So resonance curve, as I told, that when R equal to 0, this is the ideal case. It never happens actually in practice. So you will get a uh, curve like this, where at infinite it is reaching its peak, and when R is small it is like this, and it is more narrow, and when R is large you will get a flat curve like this. So drawing wise it should be the other way round. There is a small mistake here. So when R is very small you will get a peak like this, and when it is flat you will get like this. So this is how the thing will look like. Here there is a this thing should be somewhere between these two. Okay. Shapes of the resonant curve for different R's are shown. Resonant curve for smaller value of R is sharply peaked, and this circuit is sharply resonant or highly selective. Selective means it is amplifying only at that very in the neighborhood of the resonant frequency. After that it is attenuating, it is going low. But when R is high, it is having a poor selectivity. Okay, selectivity means it is selective for certain frequency, which is the resonant frequency of this circuit. So when you get a flat curve, you get a poor selectivity. So it is not recommended to have a very high resistance for the RLC circuit when you are particularly using it for any particular application, like in your transistor or in your television circuit. There you should not have a very high resistance. The ability of the resonant circuit to discriminate between one particular frequency and all others, it's called selectivity. That means, as I told, it is selective to certain frequency. Other than that, it is not responding well. So it is rejecting. Selectivity of different resonant circuit are compared in terms of their power bandwidth. So bandwidth is something like uh, how fast your system is behaving. Okay, so you won't be able to appreciate, but anyway, I just want to say that if you have a lower value of resistance, then you have a lower bandwidth, selective bandwidth. But if you have a higher value of resistance, you will get higher bandwidth. So higher bandwidth means it is allowing higher range of frequency, and lower bandwidth means it is selective, and it is selective to some small range of frequency. So that is a lower bandwidth. So half power bandwidth of a resonant circuit. What is called half power frequency? At the frequency where the power is becoming just half of that of resonant frequency, or the maximum power consumption. What is the maximum power consumption? It is V square by R at resonance, or I0 square into R. So you will get the value of the frequency F1 and F2. As you can see, this is a bell shaped curve, and it will reach the half power frequency at two different frequency where I is become 1 by root 2, or we can say it is 3 dB bandwidth. That also we can say, because this is actually, if you have the root 1 by root 2, if you take 20 log 10 of 1 by root 2, then you will get this to be minus 3 dB. So that is why it is called 3 dB. Okay. So what we want to find at this two frequency f1 and f2, you have I square r by 2, like half of the maximum power at these two frequency. So you will have a current, new current. If that current I12, then I12 square into r, that is your half power. So I12 is equal to what? I0 by root 2, isn't it, that we are getting here? Okay, so narrower the bandwidth, higher the selectivity, as we have already discussed. So half power bandwidth AV give you the measure of the selectivity. So if this is small, if this delta F is small, then it is selective. If it is high, then it is like having a higher bandwidth. Okay. So how can you solve this? You know that I0 is equal to this. I mean, select half power frequencies I0 by root 2, and that is equal to V by R, V by R root 2, that is equal to V by root over R square x square. So if you cancel VV, then you are left with 2R square is equal to R square plus x square. X is the net F, sorry, not XL, X net reactance, XL minus XC. So when you can say that a magnitude of XL minus XC is equal to R, you are supposed to achieve your half power frequency. That means if you solve for this, if you now put the value of XL here, which is omega L minus 1 by omega C is equal to R, then if you just solve it, it will be, if we divide both side by L, we get omega by omega LC is equal to R. Now if you multiply both side with omega, you will get omega square minus R omega minus LC equal to 0. So from here you can solve for omega. So what is omega 1 2? Omega 1 2 is actually 2 pi into f1 f2. So omega 1 2 is equal to plus R plus minus R square plus 4 LC, 4 into LC divided by 2. So I think it is solved somewhere. So why it is called 3 dB, that is also written here. We'll just go to the calculation part of it. So this is your equation. Okay. So from here you can solve for this omega 1 and omega 2. So it is actually that R by L, actually I missed out here when we divided by L, then I forgot to put L this side. So we are getting this equation. That means your omega 1 2 will be equal to minus R by L plus minus R square by L square plus 4LC. This is 4 divided by 2. So now what is your Q? Q is equal to your quality factor, and that I think it is not shown here, somewhere before. Q is equal to your R by L into omega 0. That is equal to your Q0. So this is the quality factor of the circuit. Or you can, uh, sorry, it is omega L into R. I mean the inductive drop by your resistive drop. So if you put that in place of L, if you replace R by L by Q0, then you get this expression for omega 1 and omega 2. And you can relate like this. You can express the whole thing like this. And omega 0 is your resonant frequency, because we know that 1 by LC is your resonant frequency. So whole thing you can replace like this: omega 1 square, omega 0 by Q0 is your R by L, because Q0 is equal to VL by VR, and this is your omega, and this is 1 by LC is equal to your omega square. So you can get the half power frequency in terms of Q0, that means quality factor, and the resonant frequency omega 0. So now at the upper half power frequency omega 2, you will get plus minus, na? Here this plus 1, if you get, you will get the uh, cap, uh, uh, the half power frequency omega 2 is greater than omega 0, and another omega 1 is less than omega 0. Okay, so this is how you can get the expression. So this is one solution. There is another solution. So when we take minus, we get this omega 1 lower frequency, and when you take plus, this is the higher than the resonant frequency. So if the quality factor Q0 is greater than 10, then the term 1 by 4 square is negligible as compared to 1, because this will be 1 by 4 into it is 400. So if you ignore this, you get this 2 as your reference frequency, your half power frequency, and then omega 2 minus omega 1 is actually this. So delta omega is equal to omega 0 by your quality factor Q0. Okay, so you can always say that Q0 is also equal to omega 0 by delta omega. So if you have a highly selective circuit, your Q0 has to be high. If it is a like higher bandwidth circuit, that means if you have omega 2, if you have delta omega is very high, then your Q0 will be equal to low, right? So for a selective circuit, your should be equal to very high. So here they are giving the expression in terms of R and L, that also they are giving. So this is your again half power frequency in terms of RL and C. And then here also, if you wish to, you can put the value of your in place of LC 1 by root LC, you can put omega 0 square and Q0 square. In that way also you can find out the expression of the half power frequency. So half power bandwidth you can find out in terms of R by L. So you can see that if you now uh, multiply with 1 by omega 0 L, then you will get delta omega by omega 0, and that is equal to your Q0. From here also we can see. So omega 1 is basically omega 0 minus delta half of the delta omega, and omega 2 is equal to omega 0 plus delta omega. So now if omega 0 is very greater than omega square, delta omega square, then you can ignore this part, and you will get the geometric mean of this half power frequency as your uh, 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 resonant frequency. So if you have a very highly selective circuit, that means highly selective circuit means very narrow kind of bell shape, then you will get, if this is your f1 and f2, then your f0 will be geometric mean of f1 and f2. But if it is a flatter one, then of course you will not get this, if this relation doesn't hold. Okay. So quality factor of an RLC series circuit is, it should be written before. It is voltage magnification, reactive power by active power. So either you can write VL0 by V or VC0 by V, because VL and VC both are same during resonance. I have written quality factor in terms of omega L and R, but you can also write in terms of this. That is also valid. Okay. So this you can write as tan phi, where tan phi is the power factor of the coil. So during resonance, your quality during resonance, what will happen? Your omega 0 you can write in terms of L and C, and you know the value of L. So we can write it as in the other way, uh, root over 1 by R into root over L by C. So that is your quality factor. Or in the other way, if you want to write through this, then that also okay. You can write 1 by R. So C divided by root over LC. So you arrive at the same expression. Okay. So from the mathematical point of view, this is the expression. But actually, the physical significance is the quality factor will talk about the selectivity here also. Okay. So if it is high, then your circuit is more selective to certain range of frequency. So that is what all we want. So maybe a few more things and problems will continue the next class, and possibly in the next class we'll conclude the resonance part. If you have any question, you can ask now. Any question? Okay. Thank you.